Previously we'd shown you how it was helpful to have a nested loop structure, and now we're going to show you a situation where you might want to have more than one parameter in the same loop. And to show that, the reason for justifying that, we'll return to the results of the single loop force versus gap parametric, where we took a solenoid model and ran it through its range of motions. And you recall that there was a huge variation in the force from the maximum to the minimum gap position. Now suppose you were wanting to control the solenoid electronically so that you could have a more constant force. The results that we obtained here assumed that the volume current, the number of ampere turns, was maintained constant, independent of the position or the range of motion of the core. Now we'll show how we could add a second parameter in the same loop where we reduce the current at each step in an attempt to get a more constant force. So to do that, once again I'll open up our gap parametric model and open up the parametric setup. Okay, so now what we'll do, we'll add a scale factor to the volume current region, which reduces the amount of current at each step. So we'll create a new parameter, and it'll be in the same loop number, loop 1, and it will be a scale volume source magnitude, and we'll call it reduction because we're going to be reducing the current at each step. Now it'll have the same number of steps as the gap parameter because it's in the same loop, and something else we'll demonstrate which you haven't seen before is the use of functions to define parameters. So in functions you enter a formula as much as you would in a spreadsheet, and the formula we're going to use will be dependent on the step number. So I'll use a formula which is equal to 10 divided by, and then brackets, I'll use the number sign. The number sign is a variable which will take on the value of the step number, and I'll add to that 9, and then I'll close the brackets. Now I have to select the coil region, and then I'll do an apply create. Okay, so the gap parameter still applies to the motion of the core, but the reduction parameter, which is the very same loop, applies to the volume current. Now if we take a look at the values of the reduction parameter, remember the formula was 10 divided by, in brackets, the step number plus 9. So for step number 1, that would be 10 divided by 10, which would be a scale factor of 1, so that would give you the full volume current. By the time you're at step number 11, that would be 10 divided by 20, you would have half the original volume current. So that's going to produce quite a reduction in the value of current from the first to the last step. Now, as before, we've already done this, so we'll open the results here. And analysis parametric results. So here, once again, we have the same 11 steps because we have only one loop, but two things are happening at each step. First, there's a change in the position of the core, and second, there's a change in the volume current, the scale value. Okay, now something else, just to get back into the parametrics for motion for a minute. One other thing I had done, I'd added another post-processing variable, which is the total current on the region, so that we could plot that after the run.